So thank you again for organizing and letting me speak here. It's a pleasure. So I want to take what you just heard from Lorenz's talk from the computations and use them to actually see how we can generate or find vacua with small w0 near the Conifold. So, sorry. So of course, the big picture, as usually, is we have the landscape and the swampland, and we have all heard that a million times before. But the big question I want to address here in a very vague way is actually, where does de Sitter lie in this picture? Of course, we know that there are good arguments that it should not lie in the landscape, but still there's a certain idea that maybe our universe is actually de Sitter, so should it not actually still be part of a landscape? Instead of looking at the big picture here, I want to be a little more conservative and look at the little picture, and first ask, well, where does actually KKLT lie in this picture? So KKLT is, in its base, a recipe for de Sitter. A recipe that, when it was written down, it was never actually cooked. So we have this, so the starting point is already something which is a very weird ingredient, because it's more like using an alien life form for our pie, because small w0 is actually something that, statistically speaking, should be there, but nobody, until very recently, nobody had actually seen it. But assuming it's there and we can use this ingredient, we want to put in a couple of teaspoons of non-perturbative effects in order to find our first basis of this recipe, the AdS vacuum. Of course, we want to end up in a de Sitter vacuum, so we need to uplift this AdS vacuum using some anti-D3 branes, probably. And in order to have this uplift be very small, we also want to live in a conifold or another region of strong warping. However, of course, this strong warping should also be there from the very beginning. So we need to also analyze the W not smaller than 1 ingredient in a strongly warped setting. So in the last couple of years, of course, a lot of people have worked on this stuff. These are just a few of these people. I tried to fit in all of them, but that didn't really work. But today I want to, I want to talk about the first 2 ingredients, the basis of our recipe, which is small w0 at the conifold. Recently, Dimitas, Kim, McAllister, and Moritz have constructed a method to find small w0, but that was completely at the large complex structure point. And I want to tell you about our generalization of this algorithm to the conifold. As Lorenz already mentioned, at the same time as we were working on this, Dimitas, Kim, McAllister, and Moritz, which I will call DKMM for brevity, also published their version of this algorithm. If time remains, I want to also talk a little bit about KKLT, this AdS minimum in particular, and the Swampland conjectures. So let's start with the general recipe for W0 smaller than 1. The idea here is that small values can actually naturally be generated by perturbative mechanisms if the leading term of this perturbative expansion vanishes analytically. And the key observation here is that if we are at weak string coupling at large complex structure, and if everything is expressed in terms of mirror variables, the pre-potential of the complex structure moduli does in fact split into a classical and a non-perturbative part. This means we have a pretty clear to-do list in order to find a small value for W0, which is, first of all, we need to find fluxes, which solve the perturbative F-term equations for W0 equals 0. And then we will use the non-perturbative part to generate a small potential for the remaining flat direction, which, as we will see, is parameterized by the axis dilaton. The setup here is an orientifold of a Calabi-Yau threefold wrapped by a number of D7 brane, which carries some D3 charge. We assume we have a period vector in a symplectic basis. This period vector, of course, comes with a prepotential such that the second half of the periods are given by the prepotential. And we will always work in inhomogeneous coordinates here, such that the first period is just 1, and the dependence of the first B period is then, of course, modified, the dependence of the first B period on the prepotential. Then we can see that, or we have seen that the prepotential does split into a perturbative and an instanton contribution. And if we include the axiodilaton into our story, we can write the scalar potential and the superpotential as is shown here. The first part here is the perturbative prepotential. In this formulation, it is just a cubic polynomial in the moduli, and all of the parameters here are given by the structure of the mirror Calabi-Yau. So DKMM nicely formulated a lemma which guarantees the existence of what they called a perturbatively flat vacuum by a couple of equations that a pair of integer vectors have to satisfy. First of all, these integer vectors actually determine the fluxes that we will choose in the end. So the first equation they should satisfy is the tadpole bound. The next two equations here are just the F-term equations and W equals 0 in the minimum. In this minimum, in this generic minimum, we find that the moduli are just linear in the axiodilaton, and this linearity factor P should lie in the Kähler cone to have a trustable minimum. Of course, these fluxes should also be integer valued, and this is the last of the conditions. In the last step, we want to include the instanton contributions to this perturbatively flat minimum. At large complex structure, the instanton list is, sum is just sum of exponentials in the moduli. Of course, in the perturbative minimum, all these moduli are just linear in the axiodilaton, and the effective superpotential is then also just a sum of exponentials in the axiodilaton. We should be able to nicely minimize this to a small value by a racetrack-like procedure if the two leading instanton contributions are similar enough in this way. Now, this was the stabilization to W0 smaller than 1 at the large complex structure point. Now we want to look at how to go to the conifold with this. Actually, the hardest part, which Lorenz talked about, is actually finding the periods and the prepotential at the conifold. I just want to, for those who came later or want to watch this on YouTube, just mention the difference between the two methods that DKMM and we used to determine these periods and prepotential. The first method is by DKMM and very nicely avoids the complete computation of the periods. However, they can only look at a couple special cases, which is when the conifold cycle is mirrored to the shrinking curve on the mirror dual side. Also, I want to mention that their solution is not a full solution. They are missing one of the periods, which means that in the end, for the scalar potential, we only have good approximations, but cannot calculate the minimum numerically. Our method, however, is a slightly more general method, and as Lorenz already said, in principle, it's a very general method. And we do have a complete solution, so we do have all the periods, and thus we can check the approximations numerically in the end. However, finding these periods is a fairly involved computation. So as Lorenz already said, we are looking for a transition matrix from a local basis omega to the symplectic basis large pi. And at large complex structures, monodromies fix this uniquely. However, at the conifold, this is not enough. We have to analytically continue and match coefficients in order to find this transition function. As we were able to rewrite the fundamental period as a hypergeometric function, we were able to analytically determine this transition matrix at the conifold. And with this matrix, we can then efficiently compute periods at the conifold to very high order, as well as prepotentials and mirror maps. So how do we use this? Our setup, once again here, we are in an n-parameter Calabi-Yau orientifold this time, where one modulus is now close to the conifold, the other moduli are at large complex structure. In the notation I will use here, once again, we're in inhomogeneous coordinates, so x0 is 1. The rest of the A periods are given by are ordered as follows. The first, we have the large complex structure moduli here, and then the last of these periods will be the conifold modulus. So note that the I and the alphas run over different numbers. Alpha in particular only runs over the large complex structure modulus, and I or J also run over all of the moduli. The prepotential here is then generally given also once again by a cubic in all the moduli, and the typical z squared log z term we find from a conifold. This is probably known to most from the quintic already. The instanton contribution looks a little bit more complicated here. We have once again a sum over the curves, but then we write this instead of the exponential term because the large complex structure moduli are still just exponentials in these QI. However, or the QI are just exponentials in the large complex structure moduli rather. However, the conifold modulus enters linearly or polynomially. Now we have one type of modulus more, so we have a 3-step to-do list. Once again, we first find fluxes that solve the perturbative equations for W0 equals 0, but we choose to do this directly at the conifold locus at Z equals 0. In the second step, then, we want to stabilize the conifold modulus to a small value, and we will find that the superpotential in this minimum will not be 0 anymore, but it will at least be order Z. And finally, again, we include the instanton corrections for the remaining flat direction, which again will be parameterized by the axodilaton. Our first step, of course, is to choose fluxes. In order to find a nice general form for the minimum, we want to have a superpotential of degree 2 in the large complex structure moduli. And this already completely determines the form our fluxes should take. Note that in order for us to have integer fluxes, also these combinations of fluxes and the structure of the Calabi-Yau should be integer, which also means that the BI and AI alpha have to be rational. These are the rationality conditions that Lorenz was alluding to. Note already here that I and alpha do not run over the same number of indices. And the first step is to stabilize the large complex structure moduli at Z equals 0. Doing that, we find that this is just the superpotential, and stabilizing it to vanishing superpotential, we find on the one hand, the large complex structure moduli are again linear in the axodilaton, and we find additionally a condition on the fluxes. This is exactly as in DKMM in the original paper for large complex structure, except that here this I is running over the conifold modulus also. So in order to calculate this, since P is dependent on n minus 1, this combination of fluxes and structure of Calabi-Yau has to be invertible. In the second step, we want to integrate out the moduli. In general, the superpotential takes this form, and as we see, since we stabilized everything with z equals 0 to vanishing superpotential, the effective superpotential is of order z, and the Kähler derivative will then be in leading order just the normal derivative of w. This can be easily minimized, and this is what we find. So z, the Conifold modulus, is exponential in the axiodilaton, and the superpotential in this step is actually of order z. In the final step, then, we have instanton contributions, which we want to look at and see if we can find a racetrack-like behavior. Indeed, we have already stabilized the complex structure moduli. So U is proportional to S, and Z, the Conifold modulus, is proportional to the exponential of S. But since we since I said already that the Conifold modulus enters linearly or polynomially into the instanton series, the effective superpotential we get for the axiodilaton is in fact also just a sum of exponentials. So once again, this should be able, one should be able to stabilize this in a racetrack-like manner. However, this has to be checked case by case. Speaking of case by case, let's just look at an example. I will use the 3-parameter Calabi-Yau that Lorenz introduced here. I have written the superpotential in a slightly different form. Here, the first block here is determines the perturbative prepotential, and the leading instanton contributions are given by this series, where here already we see that these Qi are exponentials in the large complex structure moduli and polynomial or in the Conifold modulus. Bi and Ai alpha have to be rational. This is okay. A33 is irrational, but that doesn't matter since alpha only runs from 1 to 2 here. Then after steps 1 and 2, after stabilizing the complex structure moduli, we indeed see that the Conifold modulus is much smaller than 1 if the real part of S of the axiodilaton is much larger than 1, which very nicely fits in our calculation. The trustable regimes match nicely. So then we have to choose some fluxes. These have to satisfy a bunch of equations here. So we have these integer condition, we have an invertibility condition, and we have this condition on the fluxes such that W equals 0 in the first step. But additionally to this, we have to be able to trust the instanton series. So Qi, of course, have to be smaller than 1. In the perturbative minimum, all the Qi are just an exponential of S. Since we want to stabilize the real part of S to a large value, it is a necessary condition that these prefactors here are smaller than 1. Although these are a lot of different conditions, a simple search actually just finds many small fluxes, reasonably small fluxes that satisfy all of them at once. Talking about a concrete solution, one could, for example, choose these fluxes here, and one finds a nice minimum, which is, as we can see here, a Minkowski minimum with W0 of order 10 to the minus 6. Since we do have access to the full periods, we can just directly compute the masses in this minimum. Doing that, we find a very heavy mass, which corresponds to the Conifold modulus. The large complex structure moduli are also quite heavy, but the axiodilaton is a very, very light state, which makes sense since it is only stabilized by perturbative effects. It is still important to note that this mass of the axiodilaton is proportional to W0, which also sets the KKLT mass scale. So one has to be careful when starting with this into a KKLT-like scenario, because the axiodilaton cannot be integrated out beforehand. A short word on the search we did over the fluxes. It was an inexhaustive search, so no claims on actual numbers. The semi-analytic computations we did were basically the same that DKMM did in their paper. We did no numerical checks for all of the minima we found. Those were just too computationally expensive. We found of order 10 vacua with reasonably small fluxes and tadpole numbers with W0 smaller than 10 to the minus 6. We also found some flux combinations that gave W0 smaller than 10 to the minus 12, but those are numerical issues that appear then, and we are not sure if we can trust those. But 10 to the minus 6 is definitely completely fine. DKMM also have some words on a search they performed over fluxes in their paper. So if you're interested, please check it out. Okay, now that we have, what's the time? Now that we have basically solidified this connection between W0 and the Conifold, I want to just have say a couple words about KKLT, the AdS vacuum of KKLT, and the AdS distance conjecture. The AdS distance conjecture, let me just quickly state it. For an AdS vacuum, the limit of vanishing cosmological constant is at infinite distance in field space, and there is a tower of light states that appears in this limit, which is whose characteristic mass is given by the cosmological constant to some power alpha. And a stronger version of this conjecture states that supersymmetric vacua should have alpha equals 1/2. This tower of states is usually assumed to be a KK tower of some kind, and the conjecture is of course satisfied by most tree-level vacua we know. However, DGKT type vacua are counterexamples for the strong version. The strong version is particularly interesting because it completely forbids any form of scale separation from the internal and external space. However, since DGKT are counterexamples, we have looked at the situation and we have suggested that supersymmetry is the wrong distinguishing feature for the strong version. I will not go into this further here because of time constraints. But let's look at KKLT. KKLT as its AdS minimum seems to be fairly robust. The minimum is given by this by the typical transcendental equation, and the cosmological constant can be calculated in there. Indeed, we see that the cosmological constant goes to 0 when we send tau to infinity, which is at infinite distance in field space. So that is already the first check here. However, naively, the KK scale is 1/tau, which is of course much larger than any power of alpha of the cosmological constant here. So at first glance, the ADC seems violated. However, since we want to look at this all in a warped throat, indeed, the KK modes near the tip of a warped throat are redshifted, which was shown by Ralf, Lorenz, and Daniel a year ago. Then the KK modes are actually given by this formula, which up to the log corrections here satisfies the AdS distance conjecture. Now one can ask, okay, this is just one example, but what about other quantum vacua? By quantum vacua, I mean that the vacuum itself is intrinsically generated by balancing tree-level and quantum or non-perturbative effects against each other. The other prime example one has for such a vacuum is the large volume scenario, where we indeed find a very similar behavior. So once again, lambda goes to 0 as tau goes to infinity. So the infinite distance is a check. And however, here we have a KK scale, which is also given by some log correction here and the cosmological constant to some power. So taking both of these observations together, we proposed a generalization or a quantization, if you want, of the AdS distance conjecture, which states that we have to add, in a quantum version of this AdS distance conjecture, we have to add this log correction to the tower mass. And we have also suggested that indeed, instead of supersymmetry here, determining the alpha equals 1/2, it should be a vacua without a dilute flux limit. Like I said, I did not have any time to go into this in detail. So let me summarize. KKLT is a recipe for de Sitter which has never actually been cooked. Understanding the interplay between those ingredients that we want to cook together is very important, because one ingredient may change the way two other ingredients interact. What we have shown here is that small W0 can indeed be found near a conifold. And all of the progress that I am aware of has really shown no very big holes in any of the KKLT arguments yet. However, KKLT does violate, obviously, the de Sitter Swampland conjecture, but also AdS Swampland conjectures in their standard form. The interesting part is that KKLT is intrinsically quantum, and maybe this can be the reason that KKLT is able to survive against all odds. Thank you for your attention.
All right, Max, thanks for the very nice talk. We can all thank Max using our emojis. Are there any questions for Max? We have a question from Jakob.
Hi, Max. Thanks for the nice talk. Could you go to your slide 16? Yeah, thanks. Is there a reason why in your pre-potential you're not writing out the coefficient of QU2? Is this somehow harder to compute?
It vanishes.
It vanishes. Yes. Ah, I see.
So the only first order coefficient that survives is QU1.
I see. So in your examples, do we always stabilize the Conifold potential superpotential against the QU1 term in the superpotential?
Yes, in the end we did that for the semi-analytic computation of the minimum. Yes, that was the racetrack in the end, basically.
Mm-hmm. Thanks. I wanted to point out one other thing regarding the computation of the full period vector in using our method. You can still compute also the period corresponding to the cycle dual to the fundamental cycle just by integrating Euler's reflection formula. So yeah, you can still do that. I just wanted to add that.
So you can generate the full periods in your method, is what you're saying?
Yes.
Okay.
We didn't write it out because we didn't need the explicit form, but yeah.
Okay, that's very nice to know.
Thanks.